Okay, geometry section 1.4 is all about one word, and that word is distance. And we're going to learn how to measure distance in two different settings right here. But we begin with something really simple and basic called the ruler postulate. This is not something you guys really need to write down, but it is just kind of a chance for us to reinforce the idea that a postulate is a concept in math or specifically geometry that we know is true, but that cannot be proven. And the ruler postulate says something pretty basic. Every line segment can be measured, and we can do it using a number line. Now that's important because in section 1.2, we talked about the three basic undefined terms of geometry, and we wrote them out here as a point, and then a line, and then a plane. None of the three of these figures right here can be measured. A point because it's too small, a line because it's too long but also too thin, and a plane because it's too vast. It goes on forever. None of those three things can be measured. But a line segment, which we just got done talking about in section 1.3, is the first geometric figure we've talked about that can be measured. So the ruler postulate just tells us that. I want to make sure that everybody understands this notation right here. It's not a typo, and I didn't forget to put the little bar at the top. The bar at the top means line segment AB. But when you see just two capital letters together with no symbol there, what that means is that we are supposed to find the measure of line segment AB. So basically, we would go from point A to point B, so I'll call this A and this B, and there is just one line segment that connects those two, and now we can take any ruler here and kind of put the first part there at point A, and then, do I remember how to move this thing around a little bit? You can kind of tilt this a little bit if I knew what I was doing with it. Anyway, and you would started at A, ended at B, and you could measure a line segment. That postulate isn't super important. Let's talk about how to use it. The first thing we're going to do is talk about measuring distance in one-dimensional space or 1D space. And when we talk about 1D or one dimension, we're really just talking about a line here. So in this case, we have a number line. It's a line because of the arrows on the left and the right that indicate, like the set of real numbers, that they go on forever. There is no minimum and there is no maximum. But what I'm asking you guys to find right here that we're going to work through together is, let's go back to our notation right here, the measure of line segment AB. That's the first thing we're looking for right here, the measure of segment AB. Now, if I'd given you the whole number line, there would have been a whole bunch of dashes right here, I don't know how many and I don't really care, between -12 and -3, and yeah, you could sit there like a little kid and count on your fingers and go 1, 2, 3, 4, 5. It's kind of a juvenile way of doing it though, and it takes a really long time. So the simple version of the distance formula here in one-dimensional space that I want to make sure everybody has down is this, and I wouldn't even call this a formula. What we're going to do here, guys, is take your right endpoint minus your left endpoint. And if you can do that, you're going to get these problems perfectly right. Let me show you what I mean here. So line segment AB ends at point B, which is right here at -3. So going with right minus left, the right endpoint of AB is -3. So there's my right endpoint, -3, minus the left endpoint right here, which is -12. Now I'm subtracting a negative number, and I'm hoping you guys can do this without a calculator. Anytime we're subtracting a negative, that just turns into a plus. So this is really -3 plus 12, which is going to give us our answer here of 9. So again, what are we finding here? This means the measure of line segment AB is 9 units. So I'll just go ahead and put a 9 right there, and that's what that distance is from A to B. Okay, how about the measure of line segment BC? Once again, right minus left. So BC, let me switch colors here. I'm going to go to this lovely shade of purple. BC starts here at B, ends at C, and is this segment in between them. So again, right minus left. The right endpoint of BC here is 4, and we'll subtract the left endpoint, which is -3. Once again, we're subtracting a negative. 4 minus -3 simply becomes 4 plus, I was thinking of the answer, 4 plus 3, and our answer there is going to be 7 for the measure of line segment BC. And now, if you were paying attention to the segment addition postulate, which we did back in 1.3, you could probably take a look at this answer and this answer and formulate a pretty good guess as to the third question here, how long is AC? But let's try to do it the same way we did before. I'm going to go with this orange color right here, right minus left for AC. So AC ends on the right here at 4 minus, and it begins all the way over here on the left at A. So that's a 4 minus negative 12, which turns into a 4 plus 12, and we're going to get our answer now of 16. So I'm hoping here you saw this already. The 9 that we got for AB and the 7 that we got for BC, that makes a lot of sense with an answer of 16 because of the segment addition postulate. 9 plus 7 should get you that 16 we were looking for the whole thing. So that's the distance formula in one-dimensional space, guys. It's simply your right endpoint minus your left endpoint. Pretty simple and pretty easy. People always ask me, hey, do we need to know this formula? Do we need to do it that way? Or can I just count units here and come up with the answer that way? My answer to that is, if it's a relatively simple problem like the one we just did, yeah, counting will be just fine. But on a quiz or a test, we might be mean to you guys and give you some really big and ugly numbers here for those coordinates. Like instead of a negative 12, I might make that a negative 73.6. Maybe I'll throw decimals at you. And instead of a negative 3 here, that might be a positive 1.72. Now I don't think you're going to be able to count the distance between negative 73.6 and positive 1.72. So I'd really recommend that you guys take the time just to get used to this idea right here. Okay, that's all we were going to do with one-dimensional distance. It's pretty straightforward. It gets much more complicated when we start talking about the two-dimensional distance formula. Okay, so here it is, guys, and you need to make sure that you have this formula written really, really clearly in your notes in big letters and that you've got it written down exactly the way it's written here. So let's walk through it. D, which stands for distance, is equal to, and we've got this symbol right here, guys, which everybody wants to call a square root sign, and it is. Although next year in Algebra 2, you're going to learn that that symbol right there can be used for different kinds of roots, not just square roots. Cube roots, for example, fourth roots. So the real word for that symbol right there is called a radical, but you guys don't need to worry about that too much right now. You can go ahead and call it a square root sign. So distance is the square root of, and in a set of parentheses right here, we're going to take x sub 2, or usually we just say x2, minus x1, close the parentheses, meaning we do what's inside first, the subtraction, then we square that result. And then we are going to add to that. Now we do the same thing for the y coordinates that we just did for the x coordinates. Y sub 2 minus y sub 1, close that parenthesis, and then square that result. Okay, guys, that right there is the distance formula. So as long as you have it written down, that's probably good enough for your notes for right now, but I would like to explain relatively quickly where that comes from. Some of you guys will find some meaning to this. What the distance formula is useful for is finding the distance between two random points on the coordinate plane. So I'm going to just randomly put a blue dot right there, and we're going to generically call that point x1, comma, y1. Now, in a real problem, those will be numbers that will be given to you, like we're about to do a problem where the first ordered pair is 8, 2. But for now, we're just keeping things nice and vague, x1, y1. And then I'm going to pick some other random second point right there, and we're going to call that one x sub 2, comma, y sub 2. Now again, within a problem you guys are going to see on your homework, that will actually be a set of numbers right there. But for now, it's just some random things right there. And now we're going to go ahead and draw the one and only line segment that connects those 2 points. And that black line segment that I just drew represents the distance between the first point and the second point. So that is what we're trying to measure. Now, how in the world are we going to do that? Well, we're going to pretend we're in a city, downtown Chicago, for example, and if you're trying to get from point A to point B, you usually can't walk or drive there directly in a city because there's other buildings in your way. So most cities are laid out in a grid with east-west streets and north-south streets. So if we wanted to get from point A to point B, what we would probably do is get in our car and drive, in this case, straight east until I get directly under point B, and then I think I would stop right there. And at that point, I'd probably take a left-hand turn, and I'd now proceed straight north until I got to my destination here at point B. And what in the world have we just drawn here, guys? We have ourselves a right triangle. And that's really important because there's something we can do with right triangles here that I'm hoping you guys remember from last year. I'll get to that in just a second. Where we turned at this point right here is an ordered pair that I want to go ahead and label as well. And if you guys remember here, this starting point, point A, had an x coordinate right here of x1. Point B, where we're ending up, which is right here, has an x coordinate of x2. Well, this point where we turned is directly underneath point B. It's going to have the same x coordinate as point B itself. That's x2. But if we look at the y coordinates, we started right here at point A with y1. We ended up here at point B at y2. So if we go back to this point right over here, guys, its y coordinate is going to be exactly the same as this y coordinate over here. So that's going to be y1. So that's the point where we took a turn right there. And now for the fun part. If I go back to green here, you can find the distance between this point and this point right here, really, just by subtracting their x-coordinates. Take the larger x-coordinate minus the smaller x-coordinate. In fact, that's exactly what we were doing here, right endpoint minus left endpoint. Now, you can't simplify this expression at all because of the variables. So this length down here on the bottom is just whatever x2 is minus whatever x1 is. So it's ugly, but that quantity is the length of this bottom side in green of the triangle. And then over here on the right side, if we were looking at this, we would do the same trick, but with these two y coordinates right here. And instead of right minus left, we would do top minus bottom. Y sub 2 minus y sub 1. That gets you the length of this side. And now, let's take a look at what we know, guys. Let me switch back to red. We have a right triangle here, and even though it's ugly, we've got an expression that tells us the length of one leg, the length of the other leg, and the length of the hypotenuse. And what ties together the lengths of all three side lengths in a right triangle? Well, that's the Pythagorean theorem. A squared plus b squared is equal to c squared. Now, if you guys don't mind, rather than putting equals c squared at the end of this, I'm going to shift that around just a little bit and put a c squared equals in front of that. And hopefully you guys are okay with that. That's still the Pythagorean theorem. There's just a reason I flipped it around. Okay, let's fill in what we know. C is the hypotenuse of your right triangle, which in this case we've called d. So d squared is equal to A is the length of one of your legs right here. So even though it's ugly, guys, it's x sub 2 minus x1, close it and square it. There's your A squared. Plus B, which is the length of your other leg right over here, which is going to be y2 minus y1. So what we've really set up here is the Pythagorean theorem. C squared equals A squared plus B squared, and it becomes this. And the only thing we have left to do here, guys, this is called the distance formula because we want to find out how long d is. So if we look at this equation, what can we do to get d by itself? How do I undo a square? Hopefully you remember this from last year. We do a square root to undo a square. And if I'm going to do the square root of the left, I now have to do the square root of the entire right side all at once. Now the square and the square root cancel each other out, and we get d equals, and nothing else on the right side simplifies for now. So we have to write all this out. D is the square root of x sub 2 minus x sub 1, close it, quantity squared, plus, same story now, y sub 2 minus y sub 1, close it, quantity squared. And that boys and girls, is where the distance formula comes from. Now, is that super important to you? Probably not. Is it going to show up on a test? Definitely not. But in case you're wondering where all these crazy formulas in mathematics come from, I promise you they're not just made up. There's always some logic behind it, and in this case, we're building off something that we already knew to be true. We took the Pythagorean theorem right here, reworked it, and develop the distance formula from that. But again, as long as you have this in your notes, you should be in good shape. I got 3 examples to work out with you here, guys. Let's walk through it. So here we go. We're going to start off by finding, how do we read this? The measure of mn. If m is given to you by the point 8,2 and n is given to you by the point 3, 14. I am not going to graph this, everybody, because graphing is slow, it's tedious, and it's really not accurate. It doesn't really help us get the answer. We use the formula here, and when we're trying to learn a formula, the more you can make yourself write it out and say it out loud, the better off you're going to be. D equals the square root of, and here's what we wrote down on the last slide, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So now we're trying to find the distance right here. That means that we need to fill in numerical values for x2, x1, y2, and y1. Now, we haven't talked about this yet. What in the world do those variables all represent? Well, if you take a look at the 2 original ordered pairs, here 8,2 and here 3,14, this gives us everything we need. x2 means the second x coordinate. Okay, so if I look at these points, let me go to green here, guys. If I look at the ordered pair 8,2, 8 is my first x coordinate, so that's x1. 2, right next to it, is my first y coordinate, so that's y1. Let's move on to point N now, where 3 is the second x coordinate, so that's x2, and 14 is the second y coordinate, so that number is y sub 2. So as you're just getting started here, it's probably a really good idea to label x1, y1 and x2, y2. Once you get the hang of this, you'll figure that out and you won't need to label those. I think you'll be okay with it. But for now, here we go. So in parentheses, x sub 2 is what I need right here, and that's 3. So it's going to be 3 minus x sub 1, which is right here. That's 8. 3 minus 8, close it, square it. Plus, let's move on now. In the next set of parentheses, y sub 2 is right here. That's going to be a 14 minus y sub 1, which is 2. Close it, square it. Now at this point here, guys, there is no reason you couldn't go directly to your calculator if you have one of the nicer calculators like a TI-30 Multiview and type this entire expression, including the square root sign and the parentheses, into your calculator, hit enter, and get the answer in one step. It's actually not a bad skill to practice. I'm going to go ahead and slow this one down because the one I gave you here I think is not that bad. Let's see what we can do by hand. 3 minus 8 is negative 5, and then that needs to be squared, plus 14 minus 2 is 12, which needs to be squared as well. So here we go. D is the square root of. Now, notice the parentheses. They're important if you're going to use your calculator. Negative 5 squared means negative 5 times negative 5, which is positive 25. We're going to add to that 12 squared, which is 144. We'll add those two numbers together, and 25 plus 144 is 169. And I'm hoping you guys recognize something cool about the number 169. It's a perfect square. And that means, go ahead and use your calculator if you need to here, but the square root of 169 works out exactly to be 13 right on the nose. So that's our answer here, guys. We were trying to find the measure of mn, so I probably could have written mn, the measure of mn, is equal to 13. That's probably the better final answer right here, but distance is equal to 13 is correct also. All right. That is what the distance formula looks like when your teacher is really, really nice to you and gives you numbers that work out well so that you ended up with a perfect square underneath the square root sign. If we were in class, I would have you guys try problem B on your own because it works very, very similarly to what just happened in part A. I'd actually advise you to go ahead and pause the video right now, try to do part B on your own, and see how you do. Okay, so hopefully you did that. Let's take a look at where we're at. Again, let's start off by writing out the formula. D is the square root of, and we've got x2 minus x1, close it, square it, plus y2 minus y1, close it, square it. Again, guys, the more you write it and the more you say it, the better you're going to memorize it. Now let's fill in what we know. D is the square root of, and now I threw some negatives at you so the plot thickens a little bit. X2 means your second x-coordinate, which is 11 here. So that's 11 minus x1. x1, your first x-coordinate, is 3. So this becomes 11 minus 3 squared. Plus, okay, y sub 2 means your second y-coordinate, which is negative 20 right here. And then minus y sub 1, the first y-coordinate, which is negative 5. So what I'm actually doing by following the formula is subtracting negative 5. So I could write this, minus negative 5, but I would kind of prefer if at this level you guys could start to see that, kind of start to hear it come off your tongue, minus negative 5, and just automatically change that to a plus 5. So this can be a little bit tricky with the distance formula if you don't know what you're doing. The formula clearly says minus right there, but I just wrote a plus, and the reason for that is we were subtracting, but we were subtracting a negative number, and minus negative automatically becomes plus. Okay, so let's see where this takes us now. D is the square root of, and again, if you had a nice calculator, you could just type all this in at once. 11 minus 3 is 8. That's going to get squared. Not necessary to put it in parentheses, but not a bad idea either. Plus, negative 20 plus 5 is negative 15. Now, guys, if that number is negative, you absolutely need to put that in parentheses before you square it if you're going to use your calculator. If you don't put parentheses, if you just type this into your calculator, it's going to give you the wrong answer. It's going to tell you negative 225, when in reality, we're taking a negative number times itself, which should actually be positive. So you have to tell the calculator to square the negative 15 by putting it in parentheses, and then it'll give you the right answer. But I'm getting ahead of myself, sorry. So let me get rid of all that junk. There we go. All right, guys. So D equals, here we go. 8 squared is going to be 64, and negative 15 squared, negative 15 times negative 15 is positive 225. Almost done here, guys. Add up the 64 and the 225, and you're going to get 289, and you might not have recognized this one, but when you go ahead and put that in your calculator, you're going to like the answer. 289 is also a perfect square, and the square root of 289 is 17. And that is, I almost did it again. That's the answer right there. D is 17. So again, the directions said find the measure of UV. So I'll just write my answer a little more formally. The measure of UV is equal to 17. But guys, if you forgot to do that and this was your final answer, you'd get full credit for that. You know what you're doing. Okay, so hopefully you guys had some success doing that one on your own. And if you made an error, which very often happens right here, people give me the negative 225, hopefully you understand what you did wrong and what you need to do differently next time. I got one last example, and if you're sick of this, I can kind of get it, but you're going to see there's a reason I'm giving you this problem right here, and we'll see where we're at. So what's going on? Find the measure of JK if here's point J, here's point K. So once again, let's write it out. D is the square root of, we've got x sub 2 minus x sub 1, close it, square it, plus y sub 2 minus y sub 1, close it, and square it. And now in step 2, let's fill in what we know. D is the square root of, here it is, x sub 2, your second x coordinate is right there, that's a negative 7. Minus x1, your first x-coordinate, which is -1. But rather than writing minus -1, I'll just write that as a +1 and save myself a little bit of time. Plus, moving right along, y sub 2, your second y-coordinate is right here. That would be 0. And then minus y sub 1, the first y-coordinate, which is -8. So again, rather than writing minus -8, I'll just make that a +8. Close it and square it. Okay, and I just realized this problem didn't quite do what I wanted it to do. Humor me here, everybody. I'm going to change that -8 into a -9. And what that changes, okay, is that 8 becomes a 9 right there, and let's run with that. You'll thank me later, kids. D is equal to, and here we go. -7 plus 1 is -6. So let's put that in parentheses and square it. Plus 0 plus 9 is 9 squared, and I don't need the parentheses because that number is positive, but it wouldn't be wrong if you had it. So D equals, and here we go now, -6 times -6 is positive 36, and 9 squared is going to be 81. We'll go ahead and add those two numbers up now and get D is the square root of, and just so you guys can follow along with what I'm doing right here, let me go to, I'm going to go to Desmos here, everybody. Yeah, we'll do that. No, you know what? I like that other one I had. Okay, let's run with just plain old scientific Desmos. So what were we adding there? It was a 36 plus an 81. Okay, so that's going to get us an 84. No, that's not right. That didn't type in right. Let's try that again. 36. There we go. Plus an 81. Okay, and that's going to get us 117 for what's going to go, there you go, underneath that radical. Square root of 117. Now, the reason I changed this problem, guys, I wanted you to see one example where the number you end up with right here is not a perfect square. So let me show you that. If I go to my calculator now and I ask it to evaluate the square root of that number, 107, nope, that didn't, I got to be careful here, 117, there you go. All right, I got this ugly decimal right here of 10.81665383. So they're not all going to be perfect squares. In fact, the first two, I tried really hard to make them work out nicely. You're welcome, guys. A lot of times, if you just randomly pick numbers, though, you end up with this. So just make sure you pay attention to your directions on a problem like this. It'll usually tell you to round to the nearest tenth or maybe the nearest hundredth. I always like hundredths, which is 2 decimal places. So that's going to be 10.82. The 1 here, the 10.81, is actually in the hundredths place, but we look past that to the 6 and round up to 10.82. So that's what I would write here. 10.82, and that would be my answer, guys. The measure of JK is approximately equal to 10.82 because they're not all going to work out perfectly, and that's why I changed that -8 to a -9. I wanted you guys to see that. All right, everybody, that's a wrap on 1.4, so let's dive into that homework and let us know how you do. Good luck, everybody.